Hello everyone, my name is Ana Correa and I will present our paper Approximating Optimal Bidirectional Macro Scheme. This work is the result of collaboration between INESC-ID, Instituto Superior Técnico in Portugal, and the Faculty of Physical and Mathematical Science at the University of Chile. The bidirectional macro scheme provides much better compression high-lead repetitive sequence than Lempel-Ziv, but is NP complete to find this optimal. In this presentation, we will describe an approach that uses a simulated annealing algorithm to obtain bidirectional macro schemes that most of the time they are two approximations of the optimal. Now we will do a simple introduction to Lempel-Ziv algorithm and macro schemes. The Lempel-Ziv algorithm was invented by two Israeli computer scientists in 1970. The idea of this algorithm is to use the text itself as the dictionary, replacing later occurrence of the string by numbers, indicating where it occurred before and its length. The idea of Lempel-Ziv is to parse sequence in the distance phrase. Suppose, for example, we have the string S. We start with the shortest phrase in the left that we never seen before. This will always be a single letter, in this case B. Then we take the next phrase we never seen, in this case is A. The next phrase we never seen before will be AB, but you already see A in the previous phrase. The next image shows the rest of the pairs. Now, how do we encode this? For each phrase we see, we stick in the dictionary. For the next time you want to send it, we don't send the entire phrase. We just send the number of this phrase. The first row gives the index of the dictionary and the second row their phrase. That is, when we are encoding the ABBB from the sixth phrase, we are encoding as the for B. This maps to ABB since the fourth phrase was ABB and we added B to it. In the end, the compressed version of the string S will be SC. In 1982, James Storer and Tomasz Szymanski present a study of exhaustive classification of macro scheme. In this study, they present the bidirectional macro scheme that partitioned the text into a sequence of phrases. So each phrase is either an explicit symbol or it can be copied from somewhere else in the text, as long cycles are not added in copy process. The following example shows a valid scheme. This is encoding for this scheme, where each tuple describes a phrase by giving a pointer to another position where the phrase occurs, the length of the phrase, and the letter that ends this phrase. For example, last phrase encodes like this: 9, 8, and $. So 9 represents the last phrase points to position 9. The size of last phrase is 8, and the last letter is $. In this work, for technical convenience, we use a special terminator letter in the last phrase. How we can see this macro is valid, because all the letters can be decoded without falling in loops. Such macro schemes can produce parsing up to log n times smaller than Lempel-Ziv, but unfortunately, finding the optimal bidirectional macro scheme is NP complete. For example, we have this scheme that is valid, but this optimal bidirectional macro scheme? No. So for that we need to remove the letter of position 7 and merge with the first phrase and the second phrase. That we need to create a new pointer for this new phrase. In this case, it's going to point to position 9. And the second phrase is still have the same pointer. That we can say that is the optimal bidirectional macro scheme size 3. Now let's talk about how our approach works. Local search is a heuristic method for solving computationally hard optimization problems. Local search can be used on problems and can be formulated as finding a solution maximizing a criterion among a number of candidate solutions. These algorithms move from solution to solution in the space of candidate solutions by applying local change until a solution deemed optimal is found or a time bound is elapsed. In our approach, we use an algorithm of this type to get a possible macro scheme that is very close to optimal. The algorithm that we chose was simulating annealing. In 1983, this approach was used for a solution of the travel salesman problem. The simulating annealing algorithm was originally inspired from the process of annealing in the metallurgy. Annealing involves heating and cooling material to alter its physical properties, due to change in this internal structure. As the metal cools, its new structure becomes fixed, as a result causing the metal to keep its new received properties. Its algorithm contains a temperature variable to simulate its heating process. Initially, this variable contains a very high temperature, and then allowed to slowly cools as the algorithm runs. Its algorithm starts with the initial solution, and for each iteration, it generates a random neighbor solution. When this neighbor solution is the best solution that the previous is always accepted. If it's not, and given a probability, it can be accepted or rejected. While the temperature variable is high, the algorithm will be allowed with more frequency to accept solutions that are worse than our current solution. It gives the ability to jump out of any local optimus it is finds itself in the early stage. As the temperature is reduced, the probability of accepting your solution is small, therefore allowing the algorithm to gradually focus in your area of the search space, in which hopefully is close to optimal solution. Its gradual cooling process is what makes the simulating annealing algorithm remarkably effective at finding a close to optimal solution when is dealing with a large problem which contains many local optimus. We use the simulated annealing to find a small bidirectional macro scheme that is closer to the optimal. Each iteration of the simulating and annealing, we start with the configuration, and we obtain a number configuration by merging or splitting phrases. A configuration that merges two phrases is a valid macro scheme is always accepted. A configuration that we need to split may be accept or reject depends on the current temperature, the increase of number of phrases, and the random number choosing uniformly from 0 to 1. The equation that is present holds this decision. How this approach works. Firstly, the algorithm calculates the hot temperature and the cold temperature that is going to use and receive the number of iterations and the initial configuration. In this case, we receive a valid macro scheme. So let's see an example of this approach. So we have this configuration. We execute a merge operation, and the result is the first phrase. So now we need to create a new pointer. After 4 attempts to create a valid pointer, we have to add invalid pointer. So we're going to add a pointer that's going to lead to a loop. In this case, the first phrase is going to point to position 6. So in that will be captured in the loop of the position 21. Why? Because this configuration is not possible to decode the letter in the position 21 because it's getting the capture in the loop that involves the position 11 and 6. And with the pointer that we introduce, the new pointer that we introduce, is going to be capturing this loop. So we need to break this loop. How we do that? So first, we choose randomly a position of the loop. In this case, we have 11 and 6. So we choose 11. This position becomes an explicit letter of the macro scheme, and this operation just produce a sub phrase. In this case, it's the left phrase, and the left phrase never needs to change the pointer, so they retain the pointer. In this case, the pointer of this left phrase is going to the position 3. But if the split operation generate a right subphrase, we need to change the pointer, but it's a simple operation. So the right pointer is equal to original pointer plus the length of the left subphrase. So you just need to move the pointer. You don't need to look and search a new pointer for this subphrase. And this operation, the split operation, is much simpler than the merge operation. In our approach, we use suffix array to search copies or occurrence of the given phrase. In general, this operation requires m log n time for the phrase of the size m. To improve this time, we had two optimizations. First, we catch all the search by storing the result suffix array intervals. And when the phrase is split, this information is discarded because these intervals, they are not valid. When two phrases get merged, we combine the two intervals in the O logged n time by using inverse suffix array and a binary search. Checking for loops maybe take a considerable time, since the decompression paths can be long. So we use the linked tree data structure, which detects loops in only O logged n amortized time per letter. Since in the valid macro scheme it's possible to decode the letters at the very position, the decoding paths can be represented as a florist, where the roots of the tree correspond to the position that stores explicit letters. So here we can see example of the linked tree that you use in our approach. For example, we have this macro scheme, and now we have the linked tree structure that represents the paths of this macro scheme. So the roots of each tree is the explicit letters. B, A, B, in this case is position 7, 12, 13, and 22. And we have the presentation of the pointers. So the position 1 points to position 6, we have here. The position 8 points to position 16, this way. And the position 14 points to the position 9. We have here. So let's see how the linked tree and the split operation works. So the splitting phrases are very simple and efficient. You just need the cut operation. How does this work? Let's go see this example. So we have this tree, and now we do a split operation that's going to add the letter in the position 14. So the 14 has a connection to as a parent 9. So we need to cut this edge, and now this tree, the tree of the position 14, is going to be independent tree, whereas the root of this tree will be at the position 14. We can see in this example. So we have the letter 14, we delete the connection to the parent, and now she's a let's see how the linked tree and the merge operation work together. So merging phrase requires more modification to the linked tree because it's necessary to change all the pointers of the new phrase. So we have this example, right? We have this macro scheme, and we have done merging operation in the second phrase, and now we need to remove all the old pointers. In this case, we have this tree that is a old tree, so we need to remove a old pointer. So you have the position 8, you go into the position 8 and cut. Position 9 and cut. 10 cut. 11 cut. So now that we cut all these edges, each position becomes the roots of their trees, right? And now we choose a new position to point. In this case, let's choose the position 3. And before we create this pointer, right, we're going to Lincoln tree and ask, exists any link between the position 8 and the position 3? Exists. So we have this one. With that, if we create a new pointer, we'll make this macro scheme invalid because we'll create a loop, right? We have this one, and we'll create, this one. So we have to choose another position and try 4 times. If after the 4 attempts to create a valid pointer they fail, so we can create this pointer and go into the split operation. Given that our approach never starts by splitting phrases, it maybe gets stuck in the local minimum. And this happens in our tests. Still, the particular structure of a minima turns out to be relevant. In this minima, merging any 2 consecutive phrases results in a phrase that is unique, that is, it happens only at this position. We'll now prove that such configuration is true approximation to the optimal macro scheme. So the first theorem is any configuration where every pair of consecutive phrases is unique is a true approximation to optimal macro scheme of the sequence. So the proof of this theorem is consider the concatenation of any consecutive phrase, which by hypothesis is unique in the text. Such text substring cannot be inside the phrase of any macro scheme, because in that case should occur somewhere. Thus, every 2 consecutive phrases in your configuration must contain a boundary in any macro scheme. In this image shows such a configuration and illustrates approximation argument. So in the top string shows the local minimum macro scheme such that merging adjacent phrase creates a unique substring. In the middle shows the configuration that is obtained by merging pairs of consecutive phrases, but is not a macro scheme, therefore is not an optimal macro scheme. In the bottom it shows an optimal macro scheme. So the second theorem is for any configuration where every pair of consecutive phrases is unique, the set of the final phrase position is a attractor of size at the most 2 gamma. So how do we prove this? First, the set is attractor because by definition of macro scheme, any substring that is completely inside the phrase must have another occurrence contain an explicit symbol position. To see that its size is at the most 2 gamma, consider again the concatenation of any 2 consecutive phrases, which by hypothesis is unique in the text. Therefore, any attractor must contain a position inside the phrase. If there is a odd number of phrase, then there must also be a attractive position at the end of the text to cover the terminate dollar. Even though this condition is not always obtained, it does occur several times for some classes of strings. For these classes, is an improvement of all log the approximation provided by Lempel-Ziv algorithm. So we test to approach convergence speed with Fibonacci, 2-Morse, and binary divergent sequence, as well as on string obtained from a generator that we developed for this purpose. So for the divergent sequence, we did obtain the two approximation condition. In fact, the ratio is even better because for this test, the minimum size is 103, and we get macro schemes with this size below of 200 iterations. But unfortunately, for this type of string, our approach needs more phrases to encode than the Lempel-Ziv. So for the Fibonacci string, our algorithm quickly reached the optimal number of phrases and obtained configuration that requires much fewer phrases than the Lempel-Ziv. In this case, Lempel-Ziv, size of Lempel-Ziv is 13, and the size of the macro scheme is 3. But it seems that sometimes he needs all the iterations of the simulation, simulate annealing, because this stuck in the configuration that they need to insert more symbol, but the temperature of the algorithm is very cold, and therefore does not allow to these insertions. So for the strings that we generate, we did achieve the two approximation condition several times. And when this condition is obtained, we don't need to execute all the numbers of iterations of the algorithm. We can see that in several iterations we obtain less phrase than the Lempel-Ziv. So for the 2-Morse sequence, our approach produces macro schemes much smaller than the Lempel-Ziv, but we not obtain the two approximation condition. For this example, the 2-Morse strings, the minimum value that we obtain is 11, so the size of macro scheme is 11, and the lower bound that we know for this sequence is 4, so for that we don't achieve the two approximation condition. In this work, we have shown that the smallest macro scheme and NP-hard compute measure of compressibility can be practically approximate for some highly repetitive families of strings. So in your test, on most of the times, we obtain much better approximation than Lempel-Ziv algorithms. For the future, we want to create a compressed Lincoln tree because the Lincoln tree is storing all the letters of the text. We want to use a compressed fixed array to use less memory, of course, test with large files, and improve the simulating annealing to obtain better results.